Just going to go through an example using this mass defect. Just as I forgot to say that when you do an exam question, if it asks you for the definition of a mass defect, you write this equation down and then write down what everything means. So Z is the number of protons, MP is the mass of protons, A minus Z is the number of neutrons, Mn is the mass of the neutrons, and then M nuc is the mass of the nucleus as a whole. So here's an example. The mass of the nucleus of a bismuth atom, 212 bismuth, is 80012 U. Calculate the binding energy of this nucleus in megaelectron volts. And it gives you the mass of the proton and neutron in U. You can see they're really, really close, but actually neutrons weigh a little bit more. And it tells you 1 U is 931.3 megaelectron volts. So we're going to use the mass defect equations. We need to figure out everything. So change in mass is going to be Z. So that is the bottom number next to the bismuth. So that's 83. And then the mass of the proton is here. We then need A minus Z to find the number of neutrons. So that's going to be 212 minus 83, which is 129 times the mass of the neutrons. Then you need to take away the mass of the nucleus as a whole, which is given in the question. It's this number here. Substitute all of that into your equation. You can calculate it all in one go, but remember to put this in brackets. You don't need to put the u's in, so just leave the u's out and just do the numbers. You should get 1.92255 U. We then use this relationship here. 1 U is 9.31 times 0.3 megaelectron volts to calculate the energy. That would be the binding energy, which is here. 1.92255 times 931.3 gives 1790, which is 1,800 megaelectron volts. If you want to calculate that in joules, you would do 1,800 times 10 to the 6 times 1.6 times 10 to the minus 19. Now it will give you 2.88 times 10 to the minus 12 joules. That is how much work you would have to do to separate each of the separate nucleons back into, all the nucleons that are in the nucleus, how much work you'd have to do to separate them into individual nucleons again. And then they would increase in mass back up to what they were before. So look at this graph is incredibly important. It shows you how stable different nuclei are. And the stability of a nucleus and what leads to it being radioactive or to undergo fission or fusion is this graph. And it's how much binding energy there is per nucleon. I'm going to go back to this example I've got here. To bind the whole nucleus together, it's 1,800 megaelectron volts. So if I wanted to calculate how much binding energy there was per nucleon, I would do 1,800 divided by how many nucleons there are, which is 212. So that gives me 8.5 megaelectron volts. That means to remove one nucleon, I would need 8.5 megaelectron volts. Now, the higher that number is, the more stable the atom is. The higher the binding energy per nucleon, the more tightly the nucleons are being held on. So looking at this graph, it shows you that there is a maximum binding energy per nucleon here of iron. Iron is the highest on the graph. So iron would require the most energy to separate it into its constituent nucleons. And that is why it is made in the heart of a star. Okay, once you get past iron, if you then try to fuse to make other elements, you end up with an energy deficit and then the star dies. Okay, so that iron is the most stable. I'm just quickly looking in the book to tell me if it tells me what it is. I can't quite remember. That 8.7 megaelectron volts, okay, per nucleon. And then either side of that, it goes down. So we'll look at the right-hand side first because it's easier. So the right-hand side shows the line going down as you get bigger and bigger atoms. So if you're an element on the right-hand side of the nucleus, what you need to do is make yourself smaller to move up and become more and more stable. And you might undergo fission to do that, so splitting, or you might undergo alpha and beta decay. Okay, so you're going to go up the graph that way. If you are smaller than iron, so here, you need to increase your binding energy per nucleon by making your element or nucleus bigger. So you would undergo fusion. So these elements are undergoing fusion. Interestingly, helium-4 is higher than lithium. It's because they're equal to each other. In the lesson before, we learned about decay modes, and on that graph, if two things are equal, they're actually really, really stable up to calcium 20. So here, these are stable, okay? Back down to lithium, and then it increases again when they're equal. So you see carbon's the same there, and then oxygen 16.8, again more binding energy per nucleon than fluorine. But in general, the graph, you don't have to include these bumps. If it's asked you to sketch it, you would just sketch around like this, okay? And these are increasing their mass by fusion until they get to iron. So the binding energy per nucleon of a nucleus is the average work done per nucleon to remove all the nucleons from the nucleus. And it's a measure of stability of the nucleus. The nucleus with more binding energy per nucleon are the most stable. So if you undergo fission, the large nuclei split, the binding energy per nucleon increases in the two smaller pieces. In fusion, the small nuclei fuse, the binding energy per nucleon increases in the larger piece until you get to iron. If it asks you to work out the binding energy per nucleon and you've worked out the total binding energy, just look at the number at the top and divide by it, and it will tell you the binding energy per nucleon. So here are the questions on 27.2 if you don't have them in your book. So have a go at them, and again I'll make a help video for them. Okay. Thanks.